We're now going to answer the question, how do I write and solve addition and subtraction equations? First, I want to talk to you about equations and how they're very similar to balancing a scale. You know that when a scale is balanced, both sides are equal. Both sides must weigh the same amount. And that's what's happening in our equation. That equal sign in our equation is telling us that both sides are equal. So, for example, if I go and use my algebra tiles, maybe I'm going to use this algebra tile to say this is x, and maybe I'll use this algebra tile to represent 1. In this case, I'm actually saying that x is equal to 1, because this x over here is equal to this 1 over here, keeping this scale balanced. It's not tipping. Both sides weigh exactly the same amount, meaning that x tile must weigh the same, or be worth the same in this case, as the 1 tile. We can do that again. Maybe we'll say instead of x equaling 1, maybe it'll be x is equal to 3. If I have my scale set up like this, move this over a little bit, there we go. I can say that x is equal to 3. This x is equal to these 3 algebra tiles over here, because this side weighs the same as this side. This scale is balanced, it's not tipping on either side, so they're both worth the same amount. That x is worth 3. So we can use this idea when we write our equation. In this case, we have, actually I'll just do this. Let's see, move this back to where we started. Just move these off the scale for a little. Alright, here is an equation, an example. It looks like we have x plus 3 is equal to 9. That means on the left side of my equal sign, I have x plus 3. I'm going to put that on my scale. X plus 3 more. 1, 2, 3. Here's x plus 3, but that's on the left side of the equal sign. On the right side of the equal sign, we have 9. So I'm going to put 9 algebra tiles over here. 2, 3, 3, 4, 5, 6, 7, almost there, 8, and 9. So that's how I can set up my scale with my equation. X plus 3 is on the left side, 9 is on the right side. Notice that both sides are equal to each other, so our scale is balanced. What we can do is we can use the idea of our balanced scale to solve this equation. If we want to keep this scale balanced, we're going to have to do the same thing to each side. So think of it this way. If I were to add an algebra tile here, then I'd have to add an algebra tile over here to keep things equal. If I only added 1 to one side and not to the other, my scale would end up tipping. The same thing goes for subtraction. So if I go back to my original equation, x plus 3 equals 9, if I were to take one algebra tile off the left side, then I better take one algebra tile off the right side to keep it balanced. Whatever I do to one side, I must do to the other. That's so very important with an equation. Well, I might actually keep doing that. Maybe I'll take another algebra tile off of this side, and then I'll take an algebra tile off of that side to keep it fair. So both sides are still balanced at this point because I am doing the same thing to both sides. Maybe I'll take an algebra tile off of this side, off the left side, and I'll take another one off the right side. Guess what I have just done? I have now isolated my variable. To isolate the variable means to get the variable by itself on one side of the equal sign, or on one side of the scale in this case. And that's what I've done. I've got my x all by itself, on the left side. And now I can use this to tell us what x is equal to. X must be equal to 6 because I have x on this side, I have 6 on that side, and the equation is balanced. X is equal to 6. And you probably knew that just by looking at the original equation, because the original equation was pretty simple. X plus 3 equals 9. Obviously, x must be 6 because 6 plus 3 gives you 9. I just wanted you to see what that looks like when you balance it on the scale using algebra tiles. Not all equations are going to be that simple. What we basically did to figure out what x was equal to was we did the inverse operation. The inverse operation is when you do the opposite operation. It helps you undo what was being done. So for example, if I said that I'm adding 3, the opposite would be to subtract 3. If I'm subtracting 9, the opposite would be to add 9. I'm doing the inverse operation. And that will apply when we get to multiplication and division equations too. The opposite of multiplication would be division, and the opposite of division would be multiplication. Here, because this was an addition equation, I was adding with 3, the inverse operation was to subtract 3, and that's exactly what I did. I subtracted 3 on this side, and I subtracted 3 on that side. The related equation is how you show what we would need to do to get x by itself. In order to get x by itself, on the left-hand side, I'm going to have to subtract 3. So I had 9 on the right-hand side, and I subtracted 3 from it. My related equation is x equals 9 minus 3. Let's take a look at workbook page 229. We're going to use the inverse operation to write a related equation, and then we're going to solve for x. We're going to figure out what x is equal to. If you look at number 1, it's an addition equation. If I want to get x all by itself, I'm going to have to get rid of this 9 here. Well, right now I'm adding 9, so the inverse operation would be to subtract 9. So I'm going to get x by itself, x is equal to, and I'm going to take my 20 and subtract 9 from it. X is equal to 20 minus 9. Or when I solve, 20 minus 9, that's going to be 11. X is equal to 11. Number 2, that one is a subtraction equation. If I want to get x all by itself, I'm going to have to do the inverse operation with the subtracting 3. The inverse of subtracting 3 would be to add 3. So x is going to be isolated on the left. X is equal to 2 plus 3. I'm going to add 3 to the right side. And that means x would be equal to 5. In number 3, again, we have a subtraction equation. If I want to get x all by itself, I'm going to have to get rid of that 7. Right now I'm subtracting 7, so I'm going to do the inverse operation, which would be to add 7. And I'm going to add 7 to the right side. X must be equal to 17. Again on page 229, now we're going to write and solve the equation that each model represents with the algebra tiles. And circle the tiles that you remove from both sides. So in number 7, I see the equation x, because that's this algebra tile, plus 3, which are these algebra tiles, and that's equal to 1, 2, 3, 4, 5, 6, 7, 7, which are these algebra tiles. If I want to solve this equation, I have to get x by itself, which means I have to get rid of these 3 algebra tiles. I'm going to do the opposite of adding 3, and that means subtracting 3. I'm going to take 3 away from both sides. Remember, if this were a scale, if this were on a balance, both sides are equal. So if I'm going to change something, I have to do it to both sides to keep the scale balanced. So I now would have to solve this by doing x equals 7 minus 3. Taking the 7 algebra tiles over here, subtract 3 from them, x is equal to 4. Number 8, I see x plus 1 is equal to 6. And if I want to solve this, I gotta get rid of this 1 algebra tile so x could be isolated on the left side. The opposite of adding 1 would be to subtract 1. I'm going to subtract 1 from both sides. The related equation is x, which is isolated now, equals 6 minus that 1 algebra tile. And 6 minus 1 is equal to 5. X is equal to 5. Now we're going to make our own algebra tiles to model these equations, and then we'll solve them. And then a step that I haven't really talked about, which we kind of been doing in our head, we're going to check our answer using substitution. That's so very important, especially as these equations get bigger and bigger. You want to use substitution to check to make sure that you're doing it right. So let's see, number 11. X, I'm going to use one long line to represent that big algebra tile. And then 2 small squares for the 2, and that's equal to 6. 1, 2, 3, 4, 5, 6. So there is my setup. I guess I can make this a rectangle. X plus 2 equals 6. Now what I'm going to do is I'm going to solve this addition equation by using subtraction. I want to get x by itself, so I need to subtract these 2 algebra tiles to get x all by itself. And that means I'm going to have to subtract 2 from this side to keep it equal. So x is going to be equal to the 6 algebra tiles on the right minus 2 of them. X is equal to 4. Now here's how the substitution step works. You have to go back to the original equation. The original equation was x plus 2 equals 6. But now instead of x, I'm going to substitute 4 in to see if it works. Remember, substitute means to take the place of. I'm going to take that 4 and I'm going to have it take the place of the x. And let's see, 4 plus 2, yep, that's 6. And of course, that side is 6. So I can tell that this is correct. X must equal 4 because when I substitute it in, I get 6 on both sides of my equation. Let's take a look at number 12. Number 12, let's see, x plus 5, 1, 2, 3, 4, 5, is equal to 16. Oh boy, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, now if I want to get my x by itself, I'm going to have to get rid of these 5 algebra tiles here. But I have to be fair, meaning I'm going to have to get rid of 5 algebra tiles on that side. So x by itself on the left is equal to the 16 on the right minus the 5 that we have to take away. Obviously, 16 minus 5 is 11. X is equal to 11. Now I can check it. Remember, I'm going to go back to the original equation, which was x plus 5 equals 16. And I'm going to take that 11 and I'm going to put it in for x. And now I'm going to check it. On the left side, 11 plus 5 is 16. Obviously on the right side I have 16, and 16 is equal to 16. So x is equal to 11 because 16 equals 16. Now let's talk about writing and solving equations that each balance represents. So let's go back to our scale here. Let's see, we've got x minus 1 is equal to 5. I'm going to have to add 1 to the right side in order to balance this scale. So x is going to be equal to 5 plus 1 because I have to do the inverse operation of adding 1. And that means x is equal to 6. Over here, now I just happen to have a fraction in it. X plus 1/2 is equal to 4. If I want to get x by itself, I have to get rid of this 1/2. The inverse of adding 1/2 is subtracting 1/2. So in order to figure out what x is, I have to do 4 minus 1/2. And 4 minus 1/2 is going to give me 3.5. X is equal to 3.5. Okay. Now we're going to write an addition or subtraction equation to represent each problem on page 231, and we'll use our equation to solve the problem. Tyrell has $62 to buy a new phone. How many more dollars must Tyrell save if the cost of the phone is $89? Let D be the number of dollars that Tyrell must still save. Okay, so it sounds like he's starting with $62, and we need to add more dollars in to get our total of $89. So I have an addition equation here. I bet in your heads you probably thought, if I want to figure out how many more dollars he must save, you probably thought, okay, I'm going to take the $89 and subtract 62. And you would be correct, because you do need to use subtraction here to solve this addition equation, because the subtraction is the inverse operation. So what I would have to do to get D by itself is I would have to subtract that 62. So I'm going to do my work over here. I have to do D equals 89 minus 62. That's my related equation. And D is equal to 27. So that means he must still save $27. Take a look at number 26. Let's see, number 26 says, when a mixed number is decreased by 6 1/4, the result is 9 3/8. So we're starting with an unknown mixed number. It says let M be the mixed number. So I'm going to start with M. We're starting with this unknown mixed number, and it's decreased by 6 1/4. Decrease should tell you, hey, we're subtracting. So we're going to take our mixed number and we're going to subtract it by 6 1/4. And the results of that, meaning the answer, is 9 3/8. And now we can use this equation to figure out what the mixed number is. Let's see, this is a subtraction equation, which means the inverse would be to add 6 1/4, so I can get M by itself. So M is equal to 9 3/8 plus 6 1/4. And of course I'm going to have to work that out. 9 3/8 plus 6 1/4, common denominators. And 3/8 plus 2/8 is 5/8. And 9 plus 6 is 15. So 15 5/8. M is equal to 15 5/8. So here are the takeaways. Remember, equations are like balanced scales. You must do the same thing to both sides to keep the scale balanced. Inverse operations are operations that are going to undo each other. They're the opposite operations. So addition and subtraction are inverse operations. Multiplication and division are inverse operations. We'll get into that in our next lesson. And when you're solving addition and subtraction equations, identify what number you need to eliminate to isolate the variable. Think about what you would have to do to get the variable by itself. And then, to get the variable by itself, perform the inverse operation. Do the opposite. If you're adding to your variable, well then subtract it. If you're subtracting with your variable, then add it. And then go back to the original equation and substitute what you got for x or y or whatever your variable is equal to. Substitute it back in to check to make sure that it's a true statement. So that's a way you can go back and check.